Why does fatigue fracture lead to unexpected failures? Imagine a tiny crack slowly growing inside a metal part, invisible to the naked eye. Over time, this tiny flaw can cause a sudden, catastrophic failure. That's what happens with fatigue fractures. They develop gradually under repeated or fluctuating stresses that are often much lower than the material's maximum strength. Because of this, a component can seem perfectly fine for a long time before suddenly breaking without warning. The real trouble is that the damage builds up invisibly at a microscopic level through the initiation and growth of tiny cracks. These cracks start at stress concentrators like sharp corners, notches, surface roughness, or even manufacturing defects. Each stress cycle, like a repeated load or vibration, causes these cracks to grow just a little more. Over thousands or even millions of cycles, they slowly extend. The process is sneaky because the stress levels causing fatigue are often much lower than those needed to cause immediate failure. That means traditional strength checks or visual inspections might not catch the problem early. As the cracks grow, they stay small and localized, so the part still looks intact. But once the crack reaches a critical size, the remaining cross-section can no longer support the load. Suddenly, the part fractures in a rapid and often unexpected way. Several factors make fatigue fractures especially tricky. Design features like sharp corners or surface defects focus stress in small areas, initiating cracks. Repeated loading and unloading cause crack growth even at low stress levels, unlike a single overload event. The material itself also plays a role. Some materials resist fatigue better than others. Environmental factors like corrosion can speed up crack growth, making failure happen sooner. Early crack growth is microscopic and invisible without special tools, so the component appears fine until it suddenly fails. When the crack reaches a critical size, the remaining material fails quickly, often with a rough fracture surface showing signs of overload. From a mechanical failure perspective, fatigue fracture combines the effects of stress, material microstructure, and environmental influences. It differs from brittle fracture, which occurs suddenly without plastic deformation, or creep fracture, which happens over time under high temperature and stress. In real-world applications, fatigue fractures can cause unexpected breakdowns in critical parts like airplane wings, rotating shafts, bridges, and pressure vessels. These failures often lead to unplanned shutdowns or accidents because the damage was hidden. Prevention involves designing parts to minimize stress concentrations, choosing materials with good fatigue resistance, controlling manufacturing quality to avoid defects, and using non-destructive testing to catch early cracks. Understanding how fatigue fractures develop helps explain why some components fail suddenly after long periods of service. The damage accumulates invisibly until it reaches a point where the remaining material can no longer hold, leading to an abrupt failure that surprises everyone. This is why many mechanical failures seem to come out of nowhere, emphasizing the importance of careful design, regular inspection, and early detection methods.